live innovation. The rocket, you design it, equip it, prepare it for launch off the launch pad, and then lift off. The mission begins. Once it's in space, the rocket no longer needs the launch pad. That's what platformless means, and that's exactly how redSling works. Build your app on redSling, your launch pad. You can generate the Docker images with a click of a button. Your entire app is packaged as self-contained Docker images with everything it needs to run. Once deployed, your app runs anywhere, untethered and without redSling. Platformless. Everything your app needs to run completely independently without redSling itself. Other platforms keep you on a leash, they lock you in with runtime dependencies and require calling home to their servers. redSling breaks that model with its platformless approach. Build on redSling, deploy anywhere, run untethered. redSling is your launch pad. Build with it, launch from it, then fly, free and untethered. Platformless freedom. Say hello to redSling's all-new 3D visualizer designed for power, precision, and interactivity. Audio explore 3D product models with greater precision. Render dynamic scenes using STL and URDF files. Watch robots, bins, and sensors load instantly with real-time updates directly from back-end sources, making it ideal for simulation, planning, and collaborative workflows. Rotate individual objects or the entire scene using intuitive anchor controls and simple mouse gestures. An orthographic camera ensures accurate zooming, while flexible camera angles keep your scene always in view. Integrated lighting reveals every detail, boosting clarity and enhancing visual depth from all sides. Stay spatially aware with the embedded axis guide, rotating X, Y, and Z lines in real time.
Define object behavior with redSling's Logic Builder. Trigger movement and interaction based on real-time data or business rules. All rendering is precision optimized with improved camera stability, accurate object layering, and depth sorting. Built to be web compatible and container ready, embedded anywhere. Whether you're working on robotics simulation, smart warehouse planning, IoT deployments, interactive training, or STEM education, redSling's enhanced 3D visualizer helps you build smarter, train better, and simulate in real time anywhere. redSling 3D visualizer. Real time, real power, ready for your world.
Meet Sling AI, the brain behind redSling's no-code power. It's more than just artificial intelligence. It's intelligent application building, redefined. Build smarter. Sling AI assists as you work auto-suggesting logic, catching errors, and even generating complex workflows. Your co-pilot for intelligent development.
Think it. Sling AI builds it.
No code? No problem. Just type what you need. Sling AI translates natural language into intelligent executable data models and workflows instantly.
From words to workflows instantly.
Documentation you don't have to write. As you build, Sling AI captures your UI designs and logic flows, turning them into clean, structured documentation that evolves with your app.
Build it. Sling AI writes it.
Need structure from the chaos? Sling AI processes unstructured data from PDFs, chat logs, scanned forms, and more, and turns it into actionable insights.
Read, understand, act.
Make faster, smarter decisions. Sling AI integrates embedded AI models right into your apps, powering real-time recommendations and insights.
AI that powers every click.
Open by design, Sling AI connects with OpenAI, Google Vertex AI, and your AI stack effortlessly.
Plug in, power up.
Sling AI is agentic. It acts autonomously, navigating data, systems, and decisions, delivering end-to-end outcomes while you focus on the bigger picture.
AI that gets work done.
From banking to manufacturing, Sling AI unlocks massive value. Automate processes, reduce costs, drive productivity, innovate without limits.
Intelligence at scale, innovation without boundaries.
This is AI that thinks with you, builds for you, and acts on your behalf. This is Sling AI pure intelligence delivered.
No code, platformless power, pure intelligence.
Introducing Sling AI, the pure intelligence within redSling. With Sling AI, data modeling becomes effortless. No more building schemas manually or wiring up entity relationships. Just describe your app in plain language like, build a data model for a loan management system with customers, loans, repayments, and default tracking. Sling AI instantly returns a complete, production-ready model. Defined entities like customer, loan, and repayment fields with the right data types and logical relationships suggested embedding or referencing structures. Validation rules are automatically included. And this isn't basic scaffolding, it's a fully structured model, persisted in the database and ready to evolve with your app. From prompt to precision data models in seconds. No barriers, instant and effortless results with pure intelligence. This is intelligent data modeling. It's already here. Built with Sling AI. Only on redSling. Welcome to redSling Amplify. A breakthrough that redefines what's possible.
Hello, everyone, and a huge welcome for joining us live on LinkedIn. This is the premiere of redSling Amplify, and today we have Fraunhofer IPA presenting their AI bin picking solution to us live. Fraunhofer IPA is the world's renowned, prestigious institution doing some cutting-edge work in applied research, and we are so privileged to have Dr. Richard Bowman and Daniel Schiller join us to talk us through the AI bin picking solution and actually show you a live demo. So thank you so much for joining us, Dr. Richard and Daniel. Welcome. And welcome to everyone joining us from across the globe. And thank you for registering for redSling Amplify. So just to take you through what we are going to cover today, we will do an introduction to redSling in a few minutes, and then I will be introducing to you Dr. Richard and Daniel, and Dr. Richard will then go on to give us an overview of the Fraunhofer IPA AI bin picking solution. This will be followed by a live demo by Daniel Schiller from Fraunhofer of the AI bin picking solution. Then we will have some time for Q&A as well. So please do drop in your questions so that we can answer them in this forum. Thank you so much. And joining me today is Dr. Richard Bowman. Thank you so much, Dr. Richard, for joining us and being part of redSling Amplify. We're very privileged to have you. And Dr. Richard is the head of handling processes and dexterity research from Fraunhofer IPA, based in Stuttgart in Germany. And he has completed his doctorate, just waiting for the degree to come through, in engineering cybernetics from the University of Stuttgart. And he's also got an MSc in computer science from the Georgia Institute of Technology. His expertise is in computer vision, grasping logistics, robotics, and he's done over 60 plus publications in this field. And his focus at Fraunhofer IPA is on robot assistance, intelligent robot learning, bin picking, which is what we're going to see today, order picking, palletizing, and service robotics. Thank you so much, Dr. Richard. And
Thanks
joining
for being
Dr.
here.
Richard, thank you. And joining us today is also Daniel Schiller from Fraunhofer IPA. And Daniel is the research associate leading handling processes and dexterity at Fraunhofer IPA. And Daniel has got an MSc in mechatronic systems from the University of Applied Sciences in Munich. And he's also got an MSc in engineering cybernetics from the University of Stuttgart. Daniel's expertise is in simulation, computer vision, AI solutions, and he's got 10 plus years of experience specifically in the automotive industry and having worked with the likes of BMW and Daimler. And Daniel's focus is on bin picking, virtual robo optimization, geometric optimization, and clustered object detection, all of this which comes together in the AI bin picking solution. Daniel, it's such a privilege that you could join us today. Thank you.
Thank you for being here.
Thanks, Daniel. So spend the next few minutes just talking about redSling. And redSling is part of the AI bin picking solution. So what is redSling? And so let me take you through what redSling is, what's unique about redSling, and why we are well placed to play a part in the AI bin picking solution. redSling is a revolutionary advanced next-gen no-code platform. And it's capable of building full stack applications. You're talking front end, back end, integration, connectivity to robots, AI models, IoT devices, all of that. And it's got AI assisted development capability. And you can build web and mobile applications that are composable, scalable, and you are building this at high speed in order to transform enterprises. We're talking 10 times faster than traditional development. So redSling is our advanced next-gen no-code enterprise platform. The uniqueness about redSling is that it is platformless. redSling has decoupled the platform from the application for deployment and runtime. You don't need redSling when your application is live. The focus is on the enterprise application that you have built on the platform, and the redSling platform as such goes away. And this platform, this concept, is quite unique and is a paradigm shift. And think of it this way. You look at a rocket, you have the launch pad to launch the rocket, but once the rocket is in space, the launch pad falls off and the rocket is independent of the launch pad. And that's a similar concept here, that redSling is there to enable you to build your enterprise application, a custom enterprise application, and then redSling proprietary components are not required for your runtime. And so this is a platformless concept. And what we are doing is you are able to access redSling as a platform as a service, and you can build all your application using the builder, the logic builder, your front end, back end, your integration, all of that. And once your application is ready, you are able to click and generate a container application image. We use Docker specifically, and then you can take your Docker application image and then deploy on any infrastructure of your choosing, be it private cloud, on-prem, and this makes it really quick and easy to deploy on any infrastructure without any runtime components of redSling weighing you down, saving you time and costs as well. And this comes with enormous benefits, the platformless architecture in terms of security, because you have a complete air-gapped environment between your dev and runtime. A smaller attack surface where there's no redSling components in runtime, and the Docker containerization really helps you to provide the isolation and the increased security to your runtime as well. And with Docker containers, your applications in Docker images, you're able to scale horizontally, vertically. You're able to port it on various different environments without any compatibility issues. And of course, there is no platform runtime to maintain, and this brings huge advantages as well. So there's huge benefits from moving to using redSling's platformless architecture. And you can generate the container image, application image, just with one click, generate the Docker and deploy it on any infrastructure of your choosing. Now, this particularly has got enormous benefits, especially in the IT OT connectivity areas. OT is operational technology, where you have robots, grippers, sensors, IoT devices, and often these are in factory settings where there is no connection to the internet, or you are in 5G, industrial 5G kind of networks. And it really works well in these kind of scenarios where you are able to connect IT and OT systems very easily connected to AI models, the front end and back end, and devices are speaking to one another, and the platformless deployment works really well in where connectivity is required between IT and OT and in manufacturing settings. And one of that is the AI bin picking solution, which we are going to dive in very well. Another aspect of redSling that is used in the AI bin picking solution is the 3D visualization capability. redSling is able to read URDF, the robotic definition files, and also the STL meshes, and then render this in 3D format, which is used in the AI bin picking solution as well. So I'm going to now play a video to show you the 3D visualization capability in redSling, and you can watch that.
All-new 3D visualizer designed for power, precision, and interactivity. Audio Explore 3D product models with greater precision. Render dynamic scenes using STL and URDF files. Watch robots, bins, and sensors load instantly with real-time updates directly from back-end sources, making it ideal for simulation, planning, and collaborative workflows. Rotate individual objects or the entire scene using intuitive anchor controls and simple mouse gestures. An orthographic camera ensures accurate zooming, while flexible camera angles keep your scene always in view. Integrated lighting reveals every detail, boosting clarity and enhancing visual depth from all sides. Stay spatially aware with the embedded axis guide, rotating X, Y, and Z lines in real time.
Define object behavior with redSling's Logic Builder. Trigger movement and interaction based on real-time data or business rules. All rendering is precision optimized with improved camera stability, accurate object layering, and depth sorting. Built to be web compatible and container ready, embedded anywhere. Whether you're working on robotic simulation, smart warehouse planning, IoT deployments, interactive training, or STEM education, redSling's enhanced 3D visualizer helps you build smarter, train better, and simulate in real time anywhere. redSling 3D visualizer. Real time, real power, ready for your world.
I hope you got a glimpse of what redSling in terms of its capability, in terms of platformless architecture, and particularly the 3D visualization capability that is used heavily in the AI bin picking solution. Well, without further ado, I'm going to now invite Dr. Richard to take us through the overview of the AI bin picking solution. Over to you, Dr. Richard.
Thank you so much. And thanks also for having us here and for the kind introduction. We are happy to present our work on virtual feasibility assessment for bin picking today, which is a new paradigm in solving bin picking tasks. And before I really start with the topic, maybe let's say a few words so that you have an idea what Fraunhofer IPA is about and Fraunhofer Gesellschaft as a whole organization is about. So we are the biggest applied research organization in the world. And to give you a better understanding what this means, just think about we are the inventor of MP3. So this means we are taking new findings from science, from university, and transform this to new innovations that can go to market and help you to be better on the market, to have a better business, newer solutions, new innovations. And this is our mission. So we take new findings from science and make it available to real business. This is our mission here. And you see, there are about 32,000 employees in the world working for these goals in all aspects, not only robotics, that's what we do, but also in IoT, in life sciences, and every field of research and innovation you can think of. We have about 75 institutes in Germany and distributed all over the world as well. So like we have subsidiaries in India, in Japan, in the US, also in Europe, in Austria and in Italy, for example. So there are quite many places where you can get in contact with us. We are well known for having many patents, spin-offs as well, very successful spin-offs, and also a lot of revenues each year, so 3.1 billion recently. Our institute, Fraunhofer IPA, is located in Stuttgart. We are, as said, multiple institutes, 75 institutes distributed all over the nation in Germany and all over the world. In Stuttgart, we have comprised 5 institutes, so IPA is one of them. We ourselves run about 1,000 projects each year with industrial customers and also research projects. We have 1,200 employees and also a total budget of approximately 100 million euros per year. To give you some idea what we are working on, so like our robotics department is about 60 to 70 people working on different things. My team is working on handling operations with robotics, but we also are concerned with welding, with assembly, with safety for robots, robot systems integration, and all other topics that are relevant to real robotics operation in the real world for making business. But let's go to our team. We are 14 people working towards solutions with handling robotics. That means we have model-free and model-based picking, grasping operations with robotics. I will tell you a little bit more about the model-based approaches for bin picking in a few minutes. But we are also concerned with packing planning, to taking products in a nice arrangement into boxes, of palletizing and depalletizing, what you see in this video. I will skip the bin picking part because I will show you much more soon. But also we are concerned with empties handling, for example, which is quite interesting, in at least in countries where you have to deal with empties. And furthermore, we are also concerned with digitalization of products, so we can make very nice visualizations and scans of products, which help to run and train AI algorithms on object detection and any kind of further complicated, complex solutions, which, for example, yields scalable object detection solutions, which are usable in order picking in warehouses and other things. Solutions for mobile robotics, for example, that run in warehouses, as you see here, mobile robots that can pick up objects from shelves and store them in boxes for client orders, for example. We are also active in the field of laboratory robotics, as you can see on the bottom. So robots that retrieve chemicals from cupboards or that dose chemicals for their clients. And last but not least, all these intelligent behaviors only work really well for you if the robots can smartly set them themselves. So like you might only show them in a very intuitive way by teleoperation or by showing directly to the robot what to do. And the robot learns from your demonstration and does the real thing. So like we're also concerned with any kind of intelligent mobile manipulator like humanoids and other kinds of mobile robots that can do useful jobs in your business or in your production, for example. Even these robots can utilize buttons, for example, and press buttons, just as an example. All right, then let's get deep into the topic of today, which is bin picking. So bin picking itself is the process when you are served in your production, for example, with a box or a crate of parts that usually come in bulk, as you see in the videos on the right side, that come in bulk. You don't know exactly how they are located. They are chaotically served. You have the goal to take out one after the other out of these boxes and put them in an arranged manner into some machine, for example. So like machine tending is one of the premier application cases for bin picking. You take out single parts and put them in an ordered manner into the machine so that the machine can do some useful job with these parts. Yeah, and for doing this, we are working on this since 2003 approximately. So I was not starting this, I was just jumping into the team. And we have this in real operation in real industry since many years. I think our first installations were about 2010, 2011. So we were among the first who really put real bin picking applications into real industrial operation in the world. And since then, we developed year by year many more nice functionalities, and I will show you a couple of them today. So most important to us is always to serve really the needs of the customer. So that means our solutions are always tuned for short cycle times. We are very fast in computation, and we also consider the whole process. So in the end, it's also very important when gripping that we have an intelligent gripping strategy that doesn't collide with parts and does not collide with all the rest of your environment in the end, as you can also see in the videos. In the lower video, by the way, you also see that the robot can unload machines, as you just saw the last seconds. So this robot in the lower part is a real industrial installation that is running on 2 stations, serving the machine and unloading the machine. I'm very unlucky that I cannot show more videos from real industry operation in automotive, etc. You know, they have NDAs and they don't really like others to see what's happening. But at least you get some idea. And the upper robot is a robot in our lab showing the recent technologies we do. So altogether, to give you some overview how bin picking works, you might have seen this in real world before. Bin picking can be divided into 2 major approaches, which is model-based bin picking. That means you have a cut model of your parts that you want to separate. And this is usually the case when you are in machine tending and you need a very precise placement of your parts into the machine. There we serve you with object detection in a robust way, with automatic grasp, post prediction, with automatic gripper selection, even if you have different grippers for taking your parts out of the boxes, and a full automatic self-configuration. I will show you a little bit more about this. So this is the machine tending part where you usually have model knowledge. If you don't have model knowledge, so like in cases in warehouses or when you do kitting, so like pre-order picking or assembly set kitting in a manufacturing environment, then of course you have thousands or 10,000s of parts and you might not have models of all of them, or you might not want to set up a system for all of them. So in this case, you start working with model-free approaches that do not require any training and that can just work with any new part coming to you. This is what you see in the lower part of this slide and also on the video on the right slide. There's a robot used for order picking. And by the way, it's very fast. This is live speed, so this is not accelerated. This is a robot which is supposed to pick out the right objects from a source tote into a client tote where you really assemble some kind of order of a client. And the big idea here is that we not only in a model-free fashion take out the objects from the source box and drop them very randomly in the target box, but we are here concerned with a model-free placement algorithm that is also scanning these objects in the process, as you can see here with a camera in the middle, and also scanning the target box where is space for exactly this geometry of the object, so that we can end up with a very tightly packed target box that you can directly ship to the client because it's very densely packed. And all of this happens on the fly, ad hoc, within 50 milliseconds. So we don't know what comes to the system, but in 50 milliseconds, we decide where to put it in a target box, get a nice and dense arrangement of the parts. If we have some model knowledge in this process, because we have cameras in the process, we could scan the model from some sites, create a 3D model. We can even plan ahead. This is what you can see in the very small videos below. Planning ahead means we can already tell you in a few seconds how a total box looks like for you when you want to pack a certain set of objects in a very dense manner into a box. And as you can see, this is super fast, below 3 seconds cycle time with a gentle placement, and a lot of opportunities that you have own packing rules, for example. So this system is super versatile and already in successful operation with several clients in the market. The upper part just gives you another glimpse on new technologies available with our model-based bin picking solution, which is on the one hand handling entangled parts. So when you want to take out parts of a box, you might face the problem that these objects might entangle. So if you just lift up such parts, you might take out not only one, but multiple parts, which is not what you really want to have in your machine. And so we have a detection algorithm that sees this part is prone to an entanglement, and the path planning algorithm that is really taking new path so that the part disentangles. And as another intuitive and innovative technology, we have this one, what you see here in this video, which means usually you often see parts shipped in boxes with some additional foil inside. And we can detect this foil, segment it out, and so that we only are remaining with the 3D data of our parts that we really want to retrieve from the box. So this is all technologies that help you to have a more robust bin picking solution in the end, and succeed in having a continuous operation with high performance in your applications. But nevertheless, before you really get there to have a bin picking application which is successful in your production, for example, you often face the problem that you have to invest in such a solution. And if you invest some money into it, you have to have confidence in investing this money in a solution that will really work for you in the way you want to have it. So the typical problem we see is many people are interested in running bin picking applications, but they have to be brave enough to invest their money. And in the beginning, you cannot do much more than taking the parts of a client to some suboptimal robot system in the lab where you do some some bin picking tests with it for some days. You get a feeling, yeah, it's working pretty well, but you can never fully guarantee how it's working because you're quite limited in the time you can invest in such a feasibility study with a real robot, which is, by the way, still not the optimal solution that will be served to you in the end. So you don't really know how the final system will perform when it's installed at your site. And to really break this problem, we have created a simulation, a physics-based simulation of the bin picking process that is really telling you the physics of the retrieval of parts from boxes. And this means you can use grippers, different grippers, as you can see in the lower video already. You can use, for example, 2-finger grippers, you can use vacuum grippers and others to simulate the process of retrieving parts. And by the way, usually you have, of course, homogeneous boxes with the same parts in the box, but our system is even capable of retrieving different kinds of parts from the same box with different grippers, and it can by itself decide which gripper to take, as you can see here in this video. Yeah, by having this opportunity to really test the whole thing in simulation, we can give you some performance forecast of the system to really understand how it will work later on in the real applications. And this is quite useful. And it also comes with a web service designed by redSling, which helps a lot for setting this up in a very easy fashion. I will show you this in the next steps. So first of all, our system, our bin picking system, helps the customer a lot by having plenty opportunities of self-configuration. So in the best case, you only set up your environment as a digital twin, and the system totally sets up itself. So meaning it tunes the own parameters for the detection algorithms. It is automatically detecting grass poses on the object. So this is what you see here in the upper part, that you just upload a model of your object you want to pick up, but you don't tediously have to define, I can pick it up from here and from there with my gripper that I want to use. But the system is totally by itself analyzing how this works. That's what you can see in these videos. So like for 2-finger gripper or for vacuum gripper, the system totally by itself defines where are good pickup points for these objects, which is very good because in the end, this means you are doing much simpler in setting up the system. So this means you don't need no expert knowledge, no real data for setting it up. And of course, no tedious annotation of real data to get these systems trained for your application. This makes it very easy for you to set it up. And as a byproduct, but a very valuable byproduct, you can also conduct virtual feasibility studies with this physical simulation that is also used for setting up the system. So most importantly, it gives you the opportunity without investing money into any hardware to really test your solution you might run in your production by having plenty of simulations run and analyzing what comes out of it. For example, the KPI prediction of the cycle time, of the robustness of your grass, of the placement accuracy, where you put these objects in the end. Are you accurate enough for tending your machine accurately? Um, are you having a high box clearing rate? Do you take out the last parts of the box? This is a typical problem that you might face problems in taking out the last parts of the box. And this requires a very sensitive gripper design that it really works to get to every part in the box in the end. And this is either experience of your systems integrator. So if the system integrator has good experience, they design a very good gripper for you. But if they are not very well experienced, you get the first best solution, which is not a really helpful solution for your case. And then it's much better if you can use these simulation opportunities we show here, which gives you an optimization as well for the kind of gripper you use. So you can make simulations with different kinds of grippers until you have an optimized layout for really the best performance with your system. And the system also tells you if the whole cell arrangement, like the robot, the toads, whatever is like the sensor placement and so on, is really optimal for your application. So you can optimize your system to the max before you build up any piece of hardware, which is very, very useful because I also saw in the past projects failing or taking much longer or costing more money because the first setup built up for the client was not working properly and they had to adapt a lot. And in the end, it worked well. But this pain can be avoided by just simulating beforehand and being safe with what you build up for your client in the end. And last but not least, our system, when it's once trained in this simulation, all AI's algorithms involved here are set up already in simulation and you're ready to deploy it directly on the real machine and you can run it directly. So you don't lose time. You don't have off time in your real machine in the end. You can just set up new parts totally in simulation, turn it over to the real machine, and the deployment really enables the machine to immediately start working with new parts. So no off time in your production when you want to change to new parts, which is very, very useful. So next one is just showing you how easy it is to set up. And Daniel will guide you through this process later on step by step. So on the left side, you see this is our web-based client where you can set up the robot in your system, the gripper in your system, the sensor you use, which kind of bin you're taking into the system, which work pieces are there, and how your environment looks like. So you have a lot of customization of really building up a digital twin of what your system shall look like in the end and what your environment and boundary conditions are looking like. And once this is ready, then it will show you, you can just start setting up the system, doing a virtual feasibility analysis. And our backend is running these kinds of simulations with your parts then. And after a time of calculation and simulating and analysis, you will be faced with the KPIs predicted for this setup with your parts. And you can think about, is this technically feasible? Is this economically feasible with the performance I get out of this forecast? And of course, if you're not happy yet, go into the optimization loop, have the system, optimize your system for the robot cell and for the gripper layout, and in the end, be ready for deploy the thing on the real machine that you can build up with this competence and confidence. Okay, just quickly see this in real. This is our robot in the lab, retrieving parts from homogeneous and mixed boxes, as you can see here with vacuum grippers or with 2-finger grippers. And this is how you use the system. So we have user management in our web-based client that we developed together with redSling, where you can select, for example, the robot and so on. As I said, Daniel will show you more in a second. In the end, you can rearrange all the objects in a 3D viewer to put this together into the real setup that you want to run here in the simulation. So everything's super easy and intuitive. And this is fully connected to our software called BP3. This is our bin picking solution. Cloning the whole setup that you set up in the web client to a real simulation that you can see here. This is our simulation of the robot system, and conducting retrieval operations and analyzing how well it performs. And once it performs well, you can just put this on the real robot. As you can see here, this is the deployment on the real robot, and it directly conducts what you have trained to it in simulation. So here, for example, the robot is not only retrieving the parts, it's also taking the parts into some intermediate storage for quality inspection and then taking them to an Xbox or to a machine in a real operation. So just for you to understand, the whole thing is built up very modular. So this means we don't only have a very modular and nice to use web server for the user interface, where you can interact with the system in a very easy way. So without big training, even a standard user, a standard worker can use this. Everybody who can operate a tablet PC or a cell phone is capable of using the system. So you can set it up there, and it's connected to a high process controller or high level process controller that is operating the whole procedure here for training and for operation. And we have separated the whole thing from the real robot skill controller. So that means the AI bin picking solution or other solutions from other vendors are totally out of the loop here as a single module with a standard API interface. So you can just put in not only our solution, you can also put in other solutions and compare different solutions with our virtual testing environment. Because of course, in the end, there are many bin picking solutions on the market, and one fits better for one problem, one is better suited for another challenge. So in the end, our simulation even enables you to compare different solutions here. And then we connect to our simulation server, which is running the physical process simulation on the one hand, and also keeping all the data knowledge and models here, so like the simulation data, the configuration data, the KPIs you record during the tests, and the trained models in the end that you can finally deploy to the real robot system, so that directly runs there. So this is all modularized so that you can really work with this in a very flexible fashion. And as said, the whole thing can loop in different optimization cycles so that in the end, you also optimize the design of your solution here. So last but not least, it also gives you a hands-on benefit if you go this way, because in classic bin picking systems, whatever advertising says, but in reality, you always need at least 1 hour of expert knowledge until you really feel safe in operating the system. Because at least if you just set up one grasping point, this might take you 1 minute. But if you have to set up 30 grasping points because you want to really take out every object out of your bins, then this already takes you 30 minutes, and so on and so on. So in the end, if you have this self-configuration system like we have here, you save a lot of time. It's like about 84%. And of course, it's not only time savings, most importantly, you save a lot of expert knowledge time. So you don't need an expert for setting up the system. The system itself is the expert. And this is your real benefit here, because the expert is super expensive, whereas time of just waiting a few minutes while the computer runs some computation and sets up your system is much more easy to tolerate and much better for your business as well. Coming to business, just as one of our very happy customers and collaborators, I would just tell that we are working together with Liebherr Zahntechnik since 2010, 2011 in a very tight way. So they are one of our systems integrators that bought the software from us, that are working with us for a long time, have served many clients, and their clients are super happy with the solution. One of them even said this joint product of them and us is technology leading in the market. So just to give you some idea that we're working here really upfront of technology. And we also got some awards for this work together, which was really recognized well by industry. Okay, just to wrap it up, so we have many intuitive and innovative technologies in this system, and we are day by day working on more improvements and newer technologies. So be on tight what we have next for you in the next month. But just to wrap it up, so like we have simulation-based training, we have automatic grasp post definition, segmentation of any packaging materials or whatever might be in the box, so that you can just work with the real parts in your sensor data. We have AI-based, very fast detection of objects in the box. We have distinct entanglement functions. We can work with flat work pieces. So just to name a few things that we already can do with the system, and we will be capable of doing more every year. So this is a system really upfront at state of the art. So finally, because we are always asked, what is the USP of your solution? What is the advantage of using this? Our physical simulation, on the one hand, as shown, helps you to simulate all handling and grasping processes. And just to underline this is not a 3D visualization of the process. It's a real physical simulation of the grasping processes. Don't mix it up. Other vendors show you a 3D visualization. You can think about cycle times from this, but you don't know whether physically the grasping process will work or not, and whether your bins will be emptied in the end or not. This is only possible with real physical simulation that we do here. So this is giving you really meaningful forecast for your KPI before you really invest into such automation project. The automatic setup that we can give you really opens up new opportunities, because when it setups itself, you can easily put in 1,000 of parts, because now you can really scale up bin picking with many different parts, or you can change your parts on a daily basis, which is really a hard thing before. With current systems, you take maybe a half day of setting this up, and after a half day, you don't care anymore because you have the next part already, the next half of the day. So with this system, you set it up quickly, and you can really switch from part to part in a very fast fashion. The whole thing is super easy to use. Daniel will show you now at next. So even unskilled workers can set up new parts in your robot system. If you have to switch between parts very quickly, even your shop floor workers can set up a new part easily. We are, as Fraunhofer and also as our solutions, very agile and adaptive. So whatever you want to achieve, we are not the ones to sell you a system that is there as is, but you tell you our needs, your needs, and we will adapt our solution tailored to your order. This happened in the past frequently. This is why we are technology leading, because we already solved very many special things. And in the end, we are hardware agnostic. So it means you don't have a hardware vendor login. We can work with any robot arms dealer, with any make of robot gripper, with any make of sensor maker. We give you information what is suited for your parts, which is maybe not good enough, but in the end, you decide which hardware is your focus. And this takes me to the part where we put over to Daniel for the real life demo, where you see how the system works and you get some impression how easy it is to set up the system. So Daniel, now it's your turn to show how this works.
Yes, thank you, Richard. If we can switch over to my screen, where I already prepared the user interface. Yes, that's great. So just that you know, I have the screen on my left side. That's why I will look most of the time on the left side, because have to control it. Okay, so let's start and set up a simple project. The user interface looks a little bit different from the version you saw in the presentation. Of course, we are still doing updates and are improving our system constantly. So let's create a new project, just an example project for now. Here, this is our example project. Description is not so important for now. But here, as you can see, we have a quite variety of robots already available from different robot companies, KUKA, ABB, FANUC, UR, and so on. So we are not really limited here. You can see here, these robots are really implemented. It's easy to add even more based on the UIDF. This is something experts do. That's why you cannot change anything here. We have to be a little bit precise with UIDF files. So we limit the options here so you don't mess up your robot settings. See here, we have different robots already included and so on and so on. But let's go with our KUKA for now. For now, we have three different grippers prepared in the backend. It's easy to add new grippers, but this is something I would put for now as an expert thing as well. You have to be, it's simple to set up, it's fast to set up. You just have to be precise with some settings. Otherwise, you will not see any result at all and you will not know why. Camera, easy. We can work with different companies, but for now, Photoneo and Civit are generally good camera and 3D systems. Just a 3D object, just our bin workpiece. Of course, we started a new project, so we don't have a workpiece now, but let's add a new one. Of course, I prepared something. Here we have an example object we can use. Really easy. You see our object here. Actually, I think 10 gram or a little bit less. Let's increase it to 100 gram. Have it here. Here's our project. We can remove it again and add it again. Really easy to do and fast. And oh, now it's 10 gram. Our environment currently is missing the robot because I probably forgot to click on save and continue. Yes, that was the reason I forgot to click on save and continue. But actually our bin picking cell is still missing. So let's upload one as well. You need the STL files for it, but here it is. And now in the 3D viewer, quite easy to move the objects around. We can rotate them as well if we like. Do some weird things with it. Now it's completely messed up. Oh my God. Yeah, but let's go back to 0, 0, 0. I said 0, 0, 0. 0, even though let's go back with the rotation. Yes, and we are back in our default position. So even if you mess up things, it's not that hard to fix them. So we can move them manually with our mouse within the viewer or with our settings here. So yeah, let's keep it how it is for now. Now let's go to the parameters. We have simplified things a lot for the typical user. We want to give you as less options at the beginning as possible, so it's easy to set up. And we actually want to hide most of the things from the normal user. We still have them in the admin parameters here. There are quite a lot more parameters and admin expert parameters. So in case something does not work or you want to simulate something a little bit more sophisticated, we can tell you what you can change, or we can log in and set it up ourselves. For normal user, really easy. I want to have an example with 30 work pieces, 100 cycles. The start of the simulation is not so important for the starting number of work pieces, not so important for the virtual feasibility study, but for the data generation. And then we can go to the simulation and results. Okay, save and continue. Here. For now, this will not work because I didn't set up the environment in detail, and I prepared a project here. So I'll select this one. It's, as you can see here, the same thing, just with more detailed positions of all the elements. Our bin is placed correctly, as well as the robot. Parameters, 35 and 5 cycles. This looks good. And now we can start simulation. We have three different options here: our feasibility study, which that explains, our AI training for a computer vision, training-based computer vision approach, and the optimization, which is an upcoming feature we will realize based on the feasibility study. I will click on play immediately. You see now we have started simulation. Status not started yet, but now it's running. In the backend, and I will jump over to the simulation environment in a second. A lot of things start to happen. The simulation needs to set up itself. Yes. So it will start in a second, and I can explain what happened here. So we started simulation. We loaded everything we set up. We are calculating the grasping points, like Richard explained with our approach. We are calculating the important robot positions for the bin picking approach. We are setting up the path planner for this situation. Everything of this happens automatically. We wrap it up together, bring it back to BP3. BP3 now sets up itself. BP3, our bin picking solution. As you can see here, it now loaded the project, sets up everything itself, takes even the important information and gives it to our object detection server, which sets up itself again. So everything automatically, just by a click, it started to work. And you see here now, BP3 is calculating the grasping points, and the simulation is executing it. Let's jump in it for a second. Please excuse if there is some delay in the simulation. I'm currently streaming it on my PC, and we're streaming it live again. So we have a stream of a stream. So here you actually see the execution, and let's include BP3 again. So you see we are executing the grasp BP3 is calculating. So important thing to mention here as well for the object detection part. We are using here a state-of-the-art non-training-based object detection. I know I just introduced the training-based approach, but here we're using a non-training-based approach. Still AI-based, but we don't need to train a separate network before we actually detect objects. This new approach which simplifies the complete setup of the system and the usage of the system. Of course, every object detection system has its limits, but to be honest, so far in our test, we couldn't find an object we are not able to detect immediately. But in case we have, we are having problems detecting objects, we are still offering this training-based approach, so we can train an individual neural network focusing on these specific objects. Yes, and this is what we will do for quite a long time, looking at the simulation. Simulation is running, doing all the things. Once the bin is empty, couldn't find the grasp point anymore, or runs into other problems as well. Let's see if you can manage to get this one, because that's quite a hard one. Oh, yes, he did. Okay. This will happen for quite a while until the bin is empty. As you see here, additionally, we are using a new simulation environment compared to the slides you saw previously. We are using currently the NVIDIA simulation environments, Isaac Sim and Isaac Lab, focusing on Isaac Lab because it has a GPU accelerated physics calculation, not only a GPU accelerated ray tracing, but also rigid body GPU accelerated calculations. So it's way faster than usual running other systems. Yes, so important thing, hardware. I mean, we're seeing here now a simulation. It is not that hardware heavy as you might expect. Currently, this system where we run the simulation, for the people who are a little bit familiar with graphics units, we are using a 3090 Ti, which is, to be honest, not a state-of-the-art graphics unit. So even with older ones, or even with ones with less memory, we can work with it. We have a separate computer here, or separate server, where our bin picking system currently works on. As you saw in Richard's slides, it's generally really modular. So this gives us the advantage that we can exchange different aspects, we can run it on different systems, and we can split the overall hardware requirements to different things. Yes. The detection server we're using, so object detection that you aware of it, will run on a similar system. Actually, in fact, it doesn't. The current object detection server is running on a 3090 Ti as well. It's quite fast, and we actually don't even need the complete RAM of the GPU. We can work with around about 8 GB of RAM on the system, which is normal state-of-the-art GPUs have way more RAM. So this is basically all from my side. Any questions?
Wow, I must say that was super impressive, Dr. Richard and Daniel. To see you explain the solution, and also Daniel to see the actual physical simulation taking place. That is great. So one of the, I mean, I love how you highlighted, Dr. Richard, that this solution is really unique and cutting edge. There's no other AI bin picking solution out there in the whole world like the one that Fraunhofer IPA has developed, and because it has virtual feasibility and the physical simulation. And Dr. Richard, can you talk a little bit more about what's the uniqueness, highlighting just that aspect, please? Thank you.
Yeah, thank you. So the uniqueness is majorly here that all this comes together, that you have a bunch of tools which you don't find in such collection anywhere else, where you can go from model-based bin picking. So you know about your model. We even have different approaches, at least 3 different major approaches for model-based bin picking, which is a classic one, which we already solved many times in industry. We have a learning-based approach, and we have an AI-based approach without learning. So you can choose from a big selection of solutions, and one of them always works with your parts. And on top of this, we even have model-free approaches that can work with our system. Yeah, we are concerned about the whole procedure. So this is also not standard in every bin picking solution, that we are concerned with the gripping part, with the collision freeness of path, of optimization of the whole system. And in the end, the physics-based simulation that we make use of is very, very useful because we can draw so many advantages from it, from forecast before you set up a system down to quickly setting up new systems or new parts with your existing system so that you are super flexible in your production. We call it automation of automation, so that automation systems automate themselves. And this is what we do here.
Oh, that's just fantastic. Thank you, Dr. Richard. And maybe this is for Daniel. We would love to know how quickly can we set up uh, both the simulation environment and also the actual robots themselves. What timeframes are we talking about?
Yes, good question. So the simulation environment we saw here, I mean, we are now not talking about setting up a simulation, but setting up the system is capable of the simulation. To be precise here, we need round about a week. So we have to probably come to your place, check the hardware which is available, analyze it, and we have to install different things. We have to install the back end, the front end, which is all simple to use and Docker based, like the front end we saw provided by redSling. But in the end, we have to run a few tests and see if they communicate to each other. And this includes setting up of the hardware as well. Once we have the simulation working and we want to use the results in a real bin picking cell, it of course depends on where we start. Do we start completely from scratch? Then it takes quite a long time. But assume we have a basic cell already available, installation to robot, installing everything, up to 2 weeks is realistic. If you want to do some changes in the cell, like using a new camera with the approach, or just changing the robot, be talking probably around about a week. If you have a complete runnable system, you just want to install our software, we are around about 1 or 2 days. And when you just want to, what Richard already says, you have a complete system or software is installed, and you just have a new object you want to pick up, that's more or less immediately. So we are here talking about hours. So it's like upload, it's immediately it's uploaded, and then run a test if it really works, maybe fine tune 1 or 2 things, and then it's done.
That's very, very impressive timelines for such cutting edge technology. Thank you so much, Daniel. Richard, I have a question for you now. There might be customers out there that that don't have the robo systems, that they haven't chosen the robotic provider. Is Fraunhofer IPA able to help such customers?
Yeah, absolutely, absolutely. Yes, we are also advising with our experience in automation systems. So you come to us if you have no clue about how you want to automate. You just come to us with your task. You tell us what are the boundary conditions, what you want to achieve, and we can give you suggestions for useful and optimal setups for your current problem. And we also team up with systems integrators in the end because we are not a company, a standard company, as said. So in the end, we will always work with a systems integrator, either of your choice, or we propose some that will be capable of setting up the right robot cell at your place with all our fantastic software in operation.
That's great flexibility and agility. Thank you, Dr. Richard. A few more questions. How are such systems trained? This has come up on LinkedIn Live. How are such systems trained, and how big are the sample data sets?
The simple data set are, I'm not really sure what kind of data set. So when we do a simulation, we saving the results in CSV format, so it doesn't really take up a lot of space. Our project we are creating to be used in BP3 highly depends, and that's the important thing, of the size of the meshes. If we have large meshes, then the meshes in the simulation will be large as well. Currently, this complete setup and the one project, the one I just showed you, is around about 30 megabyte, nothing. And the network, there's more important, the GPU consumption, which I already explained, is less than you can fit the neural networks in an 8 gigabyte GPU. That's more important.
That's great. Thank you, Daniel. And a couple more questions and we'll wind up. One is, how do you manage with very tightly packed objects in a bin? And
Yes.
how does the system work with transparent objects? Does it work well even with transparent objects?
Both really good questions, frequently asked questions. I would answer both of them. So first, about the tight packages in a bin. This is generally always a problem. We can, if it is physical possible, we can grasp it. But the point here is to find out, is it possible? Is your package too dense? Can you even grasp the object, and how empty you will get the bin? And this is what we can handle them. And the complete reason why we do it is to find out how well it will perform, or what hardware changes you have to do so it works better. That's for the packet objects. Talking about transparent objects, that's a big thing. First of all, most of the time it depends on the computer vision system you're using, not detection software behind it. You can do a lot of things with software. We are working on it on research projects, and we have ongoing projects about this thing. But this is mainly a task for the 3D camera. We are working with state-of-the-art 3D cameras like Civit. Fully transparent objects are not visible. That's why they're fully transparent, that's for sure. But if they are semi-transparent and we have a good camera, we can work with them. Just as additional information, we are working here with 3D data. We are working with RGB images and depth images, which leads to a way more robust system overall.
Thank you. Thank you so much for patiently answering all our questions, Daniel and Dr. Richard. It's such a great pleasure to have you both on our redSling Amplify premiere on LinkedIn Live. And it's been such a great pleasure to actually showcase the AI bin picking solution, which is really groundbreaking and one of a kind in the whole world. And so thankful for both your time and also for putting in the effort to show us a live demo today. And I want to thank also all our audience, both those who've joined online and those who are going to watch this later on LinkedIn Live and on YouTube as well. I'm sure, Dr. Richard and Daniel, there'll be lots more questions. And even as people watch this video, they will have questions and they want to engage and with Fraunhofer IPA and see how they can bring this cutting edge technology to their customers So we really welcome those engagements. Please do contact us on the ticker that was shown earlier, Elizabeth.Thong. That's myself. I'm the Chief Growth Officer at redSling. So it's Elizabeth.Thong at redSling.com. So we're really looking forward to engaging with you and introducing you to Fraunhofer IPA and seeing AI bin picking solution really flourish and in factories across the world. So huge thank you, Dr. Richard and Daniel. A pleasure to have you both.
Thank you.
Yes, it was really nice to be here.
Great. Thank you. Thanks, everyone.